Okay, so Professor Luming Lee, I'm going to have to ask you in advance to try to make it shorter than you planned. And he's going to talk about neuromodulation.
It's my, great pleasure here to give a talk about my research. Compared with the previous speakers, case report, and focus on the, neuromodulation engineering. But I'm from a school for aerospace engineering. A lot of people ask me the question about how you do neuromodulation. Because, we do device equipment for the astronauts in China, and we mold the technology from the aerospace and to the medical device. I give a video show what we do. For the measuring the mass of the astronauts in the space. The equipment is designed and fabrication in my group. Also in my, it's one of the device we launched on the Shenzhou from A to 9, A to 10, and measuring the mass of the first lady Chinese female astronauts. Also, we focus on the training, research, or equipment design. So, back to my, topic. Back to the pacemaker is last century. The event of miracle event to save 1,000 million peoples, and along with this same philosophy, we stimulate. The brain. We can use the deep brain stimulation as technology to treat some of disease such as Parkinson's disease, epilepsy. This is a very good progress in the last century. I just show a video show. A patient with Parkinson's disease before implant. The device and after implant device, and this gentleman called the #1 shaking man of Hangzhou. Hangzhou is a very beautiful, city in China. This man is a very serious shaking, and after turning on the power of deep brain stimulation device, I can writing, do some things as normal. This is the user device we created in the last 10 years by inserted brain electrode in the brain and connecting with the device implanting in body to send signals to stimulate the brain. This area depends on the targeting. It's from the deep brain stimulation to vagus stimulation to spinal cord stimulation for the pain, for Parkinson's disease, for epilepsy, and then future for depression. I just show this as FDA-approved indications. This area is currently being clinical trial. But for the patients, population in China for Parkinson's disease about 2 million, epilepsy over 10 million, and depression about 30 million, and pain a lot of people. And this is also a global challenge, particularly for aged society. Also a big market. I just show the total amount of the marketing of implant microelectronics device. For the neuromodulation, maybe the 2020, almost 50% of the total device. This slide show, the patients of Parkinson's disease. 2020-30, over 50% of total, patients in China. But only smaller of patients can use deep brain stimulation device currently because only Medtronic to control this kind of technology and provided products in the world. So, in the last 10 years, we try to design fabrication device in China, and the government also supports this area. This is a national engineering laboratory for neuromodulation. And they try to, as an example for translational research on medicine. Tsinghua University charged the laboratory, and then very famous in the world for the neurosurgery hospital, we call Tiantan Hospital, as part of the laboratory and then company, to commercial the product, the device. The mission of laboratory is the first try to developing affordable device in China, and then want to build up the industry in China, and then innovation based on the cooperation between research, industry, and clinical research, including the new interface, new material processing, new fabrication or manufacture technologies, and also new indication for clinical application. We also want one mission of the laboratory, also the training the neuromodulation surgeons in China. We also try to promoting the new technologies based on the collaboration I will mention in the following. So, as in the last 10 years, we try to do, the affordable device in China based on the, industry in Chinese industry. This are sure, have the components, the electrode and the phase through and the head and how to the equipment and then the assembly and testing and a lot of things. And because we from aerospace, it's reliability is a heritage of my group. So we pay a lot of attention on how to make the device reliable. There's a implant device in the body. The reliability is a critical point, for patients. And we do a lot of, animal trial. This is just for, rabbit. We implant the device in rabbit to make sure, the safety, the sealing, to make sure the device is working. And then we move to the monkey. And we did a lot of monkey testing. We used the model for the Parkinson's disease and then to turn on power to find, the function of a device. This image shows, the device implanted in the monkey. We try to understanding, how the conditions about connection, extension, electrode. After almost 10 years, we moved to clinical. And the first clinical was launched in 2009. And the owner of State High Scientific Award 2008, the Professor Wang, is consulting during the surgery. And this gentleman is the first volunteer. He's at that time he's 51 years old. I just show the video when turn on the power of DBS and before and after. It's totally different. It's the patient's mask. It's a mask face. There's some very interesting during the London Olympic. There's a Parkinson's disease. Because it's a mask face, someone thinks it's terrorist. It's during that time it's a very, very joking problems. So after the 40 case and 44 months follow-up, we get approved of Chinese FDA. And this is, the publication show, the clinical experts to carry out, the clinical research to publish in the Neuromodulation. And so we get approved from Chinese, FDA, last year. And till now, about 600 devices implanted in the patients in China. We did the same thing is to think about the lifetime of the device, because most of the devices use mono battery, depend on the battery life. It's for self-power is very, hot point research. Use temperature difference to create electricity. Also use Mach engine to create electricity. But I know that this kind of technology, this long distance to move to clinical application. So we used the electrical magnetic coupling to transfer the technology into the body. The big problem is that that we use a reference of MRT's work to how high efficiency coupling of the electrical and magnetic coupling during the transfer of the energy. And the problem is that we work carefully to to balance during the transfer of the technology to the temperature increase because use the tank shell. There's add current and on the shell. So it increased, the temperature of device. After more 7 years research, we moved to clinical. And this is still with 55 cases of clinical trial with a follow-up out 70 months. This show, her body, a patient to use, the charger to charge a device implant in the body. We used infrared to study, the temperature on the scan, and this is a 1 year's follow-up. We show at the beginning the patient is very carefully how to charging. After that he's very experienced. He's not very carefully. So the change of temperature, the highest temperature is changed from bottom to top, and then he has very experienced, very happy to do some things. One discovery during the research is that we found is the inside the temperature and the scan temperature there's a gap, roughly 2 degree. So we can use this discovery to protection the patients finally. We can measure in the temperature. Besides, we measuring the temperature inside of a device. Only one patient over the maximum temperature. We set maximum temperature 40 because he used wrong direction during charging. This one is outside. He used this one inside. So, hopefully the rechargeable device will be proved next month. Not only DBS in my group, we also design and fabrication the VNS for weakness stimulation. Okay, thank you. And we will move to clinical, June. And we also, try to translational medicine center and the laboratory. We a lot of collaboration hospitals, and we will do DBS center, VNS center, SCS center. We try to do translational research, clinical research, and clinical application. This is sure. The hospitals, currently use our device or collaboration with the clinical research and beyond. It's nanotechnology. We also, Tsinghua University has carbon fiber nanotechnology. It's very frontier research. There are several groups in Tsinghua University. We have collaboration. We use the fiber as the material for electrode. We have found very good property. In vitro or vivo testing, we show, good property. Hopefully in the future we use, this one as an electrode. We also found, to use nanotechnology, we use nanocomp fiber, we can erase the artifacts of electrode. Finally, we can use MR testing to research, how the DBS change the brain. Also, not only as therapy tool, but also as a research tool. Besides stimulation, we can recording, the signals outside, transfer to outside. And this one hopefully will move to clinical trial end of this year. And then we use, the MR testing for the new education for Alzheimer, drug abuse, diabetes, use and different collaboration with Harvard University Medical School and Johns Hopkins University Medical School. This one show we can check for Parkinson's disease. There's a change of the brain. And also we're looking for, breakthrough technologies. I just to show, I was discussing with the professors of TU, professor of 3D battery to increase, the amount of battery, the lifetime, with the control collaboration. And so we are here. Engineering, material manufacture, information, computer measurement, and we can driving the clinical experts in China. We're looking for collaboration with neuroscience, and we're looking for collaboration with TU Israel. So this is my clinical partner of China and also, I mean, my team. Okay, thank you very much.